You think you know what an atom looks like. Everyone does. You've seen the same picture since you were a kid, a tiny dot in the middle of the nucleus and little balls going around it in rings like planets around the sun. It looks clean, it looks logical, it feels safe because it fits with how your brain likes to imagine things, small versions of big things you already know. A miniature solar system repeated over and over, building the whole universe. But here's the problem. That picture is not just slightly wrong. It's the wrong kind of picture. It makes your brain very confident about a world that does not exist. And if you try to understand real atoms using that old diagram, you will keep getting stuck, confused, and frustrated. Not because you're dumb, but because you're using a map that doesn't match the territory at all. Let's do something different. Instead of starting with the Bohr model, we'll start with a feeling. Curiosity mixed with discomfort. Imagine I walk into your classroom, erase the atom diagram from the board and say, forget it. That little solar system is a cartoon. The real atom is stranger, smarter, and more beautiful than that. You'd probably feel a bit lost for a moment. Good. That small moment of, wait, then what is it, is where real understanding begins. From here on, we're not going to treat the atom as a little machine with tiny balls. We're going to treat it as a pattern that nature allows to exist. A pattern that obeys rules so strict and so reliable that everything around you depends on them. Let's start with the simplest atom, hydrogen. 1 proton, 1 electron. This is supposed to be the easy atom, the one textbooks use to explain everything else. You may imagine the proton sitting in the center and the electron going round and round like a little moon. But if that picture were true, we'd immediately run into trouble. When something moves in a circle, even at constant speed, its direction is changing all the time. Changing direction means it's accelerating. And one of the first things you learn in electromagnetism is that an accelerating electric charge gives off radiation. It loses energy by sending out light or other electromagnetic waves. So if the electron really were circling like a planet, it would constantly lose energy. What happens to something that keeps losing energy while it's attracted to the center? It spirals inward. It would get closer and closer to the proton, moving faster as it falls, and then eventually crash into it. If you actually calculate how long this would take using only classical physics, the answer is ridiculously short. Atoms would collapse almost instantly. You, me, your desk, the air, the stars, none of it would stay in one piece. But in reality, atoms are stable. You're reading this. Your body has been made of atoms your entire life. The universe has had atoms for billions of years. That means the orbit picture cannot be a literal description of what is happening. So if the electron is not a tiny ball orbiting, maybe we say, fine, it's just sitting there, held by attraction. That sounds simple, but it also fails. If the electron were just parked in one spot, we would know its exact position, and if it's parked, its momentum would be zero. Nature simply doesn't allow that to be perfectly true at the same time for something like an electron. This is the idea behind the uncertainty principle. It does not mean we are bad at measuring. It means certain combinations of properties just aren't sharp and exact at the same time in the way your everyday intuition expects. If you try to pin down the position more and more, the momentum becomes more and more uncertain, and vice versa. Nature doesn't store a neat little list of exact position and exact momentum at the same time for the electron in an atom. So we already know two big things. The electron is not orbiting like a planet, and it is not a point just sitting still. Then what is it doing? At this point, instead of trying to draw it like an object, we change the kind of question we ask. Instead of asking, where is the electron right now? We ask, if I tried to detect the electron, what are the chances of finding it in each possible place? That might sound like a small change in wording, but it's a huge change in concept. We stop treating the electron like a tiny bead we've lost, and we start treating it like a source of possible outcomes, each with a certain probability. This is where the idea of the wave function comes in. Don't be scared by the term. In simple language, a wave function is like a chance map. It's a mathematical object that tells you how likely you are to find the electron in different places if you go looking. In some regions, the chance is high, in others, it's low, in some, it's exactly zero. Zero means that if the atom is in that particular state, you will never, ever detect the electron in those forbidden regions. The important part is this. Before you measure, the best description of the electron is not, it is at this exact point. The best description is, it has this spread of possibilities, and the wave function describes that spread. Now this creates another confusion that we need to clear up. People often imagine the electron as a little ball smeared out, like a drop of ink dissolved in water, or like a fog filling the space around the nucleus. That's still not quite right. When we actually detect electrons in experiments, we do not see a faint cloud. We see dots. We see one electron here, one electron there, one at a time. Each electron shows up as a localized event, a spot on a screen, a click in a detector. So how can the electron be both a spread-out probability map and a sharp dot when detected? The answer is, the wave function does not describe a cloud of stuff spread out in space. It describes the distribution of possible detection outcomes. When we perform a measurement, nature somehow takes that spread of possibilities and gives one actual result in one place. And if we repeat the experiment many times with the atom prepared in the same way, the pattern of dots we collect matches the probability map predicted by the wave function. This leads us to the idea of orbitals. An orbital is not a path the electron travels, it is a stable pattern of the wave function around the nucleus. It's the shape of that chance map for a particular energy state. The simplest hydrogen orbital, the ground state, is a fuzzy ball shape, highest probability near the nucleus, gradually decreasing as you move away in any direction. No ring, no track, just a smooth probability distribution. Higher energy orbitals have more complicated shapes. Some look like dumbbells with two lobes. Some have donut-like regions. Some have areas where the probability is exactly zero, called nodes. These shapes are not physical shells made of matter. They are patterns in the probability of where you might find the electron. To see this more clearly, imagine a magical experiment. You prepare a hydrogen atom in the same state millions of times. Each time you measure the electron's position and mark a tiny dot where it was found. At the beginning, after a few measurements, the dots look random. But as you keep going, a pattern appears. The dots bunch up in some regions, avoid others, and eventually form a shape. That shape, the pattern made from many individual detection events, is the orbital. It's the visible shadow of the invisible wave function. Now, why are there specific orbitals and not just any random shape? This is where energy comes in. The electron's wave function must satisfy certain rules around the nucleus. It must be stable, it must not blow up to infinity, and it must fit the mathematical equations that describe how it behaves. These conditions only allow certain standing wave patterns with specific energies. A useful analogy is a guitar string. A string fixed at both ends cannot vibrate in any random shape that lasts. It can vibrate in certain patterns. These are its allowed modes. Each of those patterns has a specific frequency, which we hear as a specific note. The electron in an atom is similar. Each allowed wave function pattern is like a note with a specific energy. Because of this, the electron in an atom cannot just have any energy. It can only occupy particular levels. When the electron jumps from a higher energy pattern to a lower energy pattern, the atom must lose energy. It does this by emitting a photon, a particle of light, with exactly the right energy to match the difference between the two levels. That energy decides the color of the light. That's why atoms radiate light at specific wavelengths. The famous spectral lines of hydrogen, the red line, the blue line, and so on, come from these exact jumps between energy levels. By studying these lines, we can identify what elements are present in distant stars. Without this quantum structure, the universe's light would look completely different. So far, we've talked about one electron and one proton. Real atoms often have many electrons. This is where another deep rule shows up, the Pauli exclusion principle. In simple terms, electrons are a type of particle that cannot share the exact same quantum state. You cannot put two electrons in the exact same seat in the atom. They can share the same orbital only if they differ in another property called spin, and even that sharing is limited and structured. Once the allowed states of lowest energy are filled, the remaining electrons have to occupy higher energy states. This stacking of electrons into different shells and orbitals is what creates the structure of the periodic table. It decides how atoms bond with each other, how reactive they are, and what kind of chemistry you can build from them. And here is something very important for your everyday life. This same exclusion rule is one of the reasons matter is solid. When you push your hand against a table, you might imagine atoms bumping into atoms like tiny billiard balls. But what's really happening is that the electrons in your hand and the electrons in the table are being pushed into configurations that the quantum rules do not allow. The repulsive electromagnetic force between negatively charged electrons and the exclusion principle together create a strong resistance to being squeezed into the same states. That resistance is what you feel as hardness. You're not touching the table in the classical sense. You're feeling the result of quantum rules saying no to certain arrangements. Now let's go deeper into the nucleus. The simple story says the nucleus is a bunch of protons and neutrons tightly packed together. Protons are positively charged. Neutrons are neutral. They are held together by a strong nuclear force. That's okay as a first step, but it's not the end. Protons and neutrons themselves are not fundamental. They are made of smaller things called quarks, which are held together by particles called gluons. You can think of quarks and gluons not as tiny balls inside the proton, but as excitations of underlying fields. As strange as it sounds, most of the mass of a proton does not come from the quark's own masses. It comes from the energy of the motion and interactions of quarks and gluons inside. According to E equals mc squared, energy and mass are two forms of the same thing. So the energy of the fields contributes to what we measure as mass. In other words, when you ask, what is a proton really made of, you eventually end up answering patterns in fields and the energy stored in those patterns. At this point, it's helpful to change our language. Instead of saying an electron is a small object and a proton is a small object, modern physics talks about fields filling all of space. There is an electron field present everywhere, a quark field, a gluon field, and so on. Particles are excitations or disturbances in these fields. When we say there is an electron in this atom, we mean the electron field has a particular excitation bound to the nucleus by the electromagnetic interaction. When we say there is a proton in the nucleus, we mean the quark and gluon fields have formed a stable bound pattern. So the atom is not a collection of marbles, it is a set of field excitations arranged in a stable way. This also changes how we think about empty space. You often hear that an atom is mostly empty space because the nucleus is extremely small compared to the overall size of the atom. If the nucleus were the size of a marble, the atom would be the size of a large sports stadium. That picture is useful for scale, but the phrase empty space can be misleading. It suggests nothing at all is there. In quantum field theory, even what we call a vacuum is not absolutely empty. The fields are still there, and they have a lowest energy state that has its own structure and behavior. In an atom, the electron's wave function extends through this region. It has non-zero probability over a large volume. So instead of thinking of the atom as a tiny ball in a big hollow shell, it's more accurate to think of it as a region where fields take on a specific, stable pattern. Now let's talk again about looking inside the atom. In daily life, you can look at things without changing them much. You can see a tree without knocking it down. But at the atomic scale, to look closely, you must use particles or light with very short wavelengths, which means high energy. That high energy interacts strongly with the system. You cannot shine a bright, sharp light on the electron without kicking it into a different state. This is not a flaw in our technology. It's a built-in feature of quantum systems. Every measurement is an interaction. When the system and the measuring device interact, they become linked. The spread-out set of possibilities in the wave function gets converted into a single recorded outcome. The detector clicked here, not there. This process is still the subject of deep research and debate about interpretation, but the practical rule is clear. Before measurement, we use the wave function to describe what can happen. After measurement, we know what did happen. Let's pause and paint a mental story to tie this together. Imagine you shrink yourself down in your imagination and try to chase the electron around the atom. You build a tiny spaceship and fly into the atom. You look for a little ball whizzing around. You wait on the left side of the atom, hoping to see it pass by. Nothing. You rush to the top. Still nothing. You're treating the atom as if it had hidden classical reality, a ball that is somewhere definite all the time. But quantum mechanics says that picture is not the right way to think. The electron doesn't secretly follow a definite path that you just fail to see. The path itself is not a well-defined thing until you set up an experiment that asks specific questions. What you can predict are the patterns of outcomes if you ask those questions many times. The electron is not a ghost, but it's also not a marble. It's a quantum object, and quantum objects simply do not behave like everyday balls and planets. So what's really inside an atom? Not little stuffed balls arranged like a tiny solar system, not empty shells with a hard seed in the center. Inside an atom is a stable quantum state, a balance of fields and forces, probabilities and rules. The electron's existence in the atom is best described by a wave function that forms allowed patterns. These are the orbitals. The nucleus is a bound pattern of quark and gluon fields. The whole structure is held together by the electromagnetic force and the strong nuclear force, shaped by principles like quantized energy and the exclusion rule. And why does all of this matter for you as a student or a physics lover? Because it explains the world you actually live in. The reason you can sit on a chair without falling through it, the reason salt dissolves in water and iron rusts, the reason stars shine and emit specific colors, the reason your phone screen works. These are all consequences of how atoms really are, not how they are drawn in cartoons. The old solar system picture of the atom is like training wheels on a bike. It helps you balance when you're starting, but if you keep them on forever, you will never ride fast or truly steer. At some point, you have to take them off and trust the deeper rules. The truth is simple to say, but hard to accept. Atoms are not things in the classical sense. They are stable patterns in quantum fields. They are arrangements of possibilities that become actual events when measured. They are like musical notes played by the universe, allowed by strict rules and repeated everywhere. The solid world you see, tables, walls, your own body, is built from these patterns. So what's really inside an atom? Fields, rules and patterns. Not little planets, not tiny gears. A deeper order that does not care if it fits into your favorite picture. And once you let go of the old picture, the new one, strange as it is, starts to feel not just understandable, but beautiful.